I record the lessons and I post them on my YouTube channel, right? So if ever you're absent and stuff, you know. Did I not post that on the, it's all math. I'll give it to you if you don't have it, but I think I put it on Canvas. If not, I'll put it on Canvas. All right. We finished last class talking about scale. What is a scale drawing? Well, that kind of foreshadowed into what we're doing today, talking about scale factors. So just kind of to reiterate, so to refresh your memory, you can have two images, two drawings that are the same shape, but they may not necessarily be the same size. So we may have to introduce a scale factor that will allow us to relate the two together. And one example that we described was a map. So back in the day, before you had cell phones and GPS and all those little things that will map them and tell you how far away and how long it's going to take you to get there and the best route and the time it will take you to get there. Back in the day, we had these big maps that we unfolded. And if you wanted to drive from one place to another, you looked on the map. And depending on how far away you were, you could determine that based on the scale. So if you had on your map from point A to point B was 3 inches, well, if you knew the scale, how much an inch represented in terms of miles, you could determine the number of miles it took. So that's kind of where we were talking about scale. So that leads me to the lesson for today, where we are actually looking at similar polygons, and we're using ratio and proportions to help us determine missing lengths, missing angles. Because if we know the scale factor, we can utilize that information to help us answer some questions. So let's go ahead and talk about, first of all, congruent polygons. And you should remember the symbol that's used for congruency. You have the equal sign with a little tilde above it. That means that we are working with the same size and the same shape. So if you have polygons that are the same shape and the same size, then you are talking about congruent polygons. Now, that's in contrast to what is known as similar polygons. So not congruent, but similar. So while you may have polygons that are the same shape, they may or may not be the same size. So while congruency and similarity deal with the same shape, for the polygons to be congruent, they have to have the same size. I did that in the wrong color. I meant to do same shape. Yeah, I did it right. I try to color coordinate for you. Similar polygons, they have the same shape. They may be the same size, in which case they are also congruent. But if they are not the same size, they are different sizes, we can only say they are similar. And the symbol to denote similarity of two figures or two things is just a single tilde. Okay? So let's talk about similar in terms of what that really means about the polygons. If two polygons are similar, this is true if and only if their vertices can be paired such that corresponding angles are congruent and corresponding sides are proportional. They have the same ratio. So you are allowed to say that two polygons are similar if these facts are true. So this is saying that the angles are congruent, the corresponding angles are congruent. And here this is saying that the corresponding sides are proportional. Proportional. There is a ratio, a scale factor relating the two. So what's important to denote when given polygons, so if you notice in this example, you are given two polygons, order matters. So this is a similarity statement. This is what we call a similarity statement. And in a similarity statement, order matters. So what do I mean by order? The order in which you are listing the vertices. So in your first polygon, quadrilateral, you have A, B, C, D. So A, B, C, D. I am starting at this corner. I'm going up to the right, down into the left. So the order that I'm traversing the perimeter is this order. So I'm starting here and I'm going this way. For polygon quadrilateral, same shape polygon, PQRS, since these two are similar, that means I am starting here and I'm going in the same order. So the order matters. I'm starting here and I'm going this way. Does that make sense? So for two polygons to be similar, the way we list them in the similarity statement, we have to pay attention to the order. We have to start at corresponding vertices, and then we travel the two figures in the same order. Again, we know them to be similar because of that little tilde. So I can find the perimeter of each of these polygons. So if I calculate the perimeter of the first one, A, B, C, D, I'm just adding the lengths of all the sides, and what do I get to be the perimeter? 10. Now, if I do the same thing here, and again, I add all four sides, I get the perimeter to be 20. So I can see corresponding angles, again, depending on which vertex I'm starting at, etc. So in other words, corresponding angles, let's look at them. So corresponding angles, angle A is congruent corresponding to angle P. What about angle D? What is that corresponding to? So angle D is congruent and corresponding to angle S. And I keep traveling. And I have angle C is congruent corresponding to what? Angle R. And then lastly, I have, looking for another color, angle B is corresponding and congruent to angle Q. Okay, so I could list my corresponding angles knowing that they're congruent because these are similar polygons. Now, the ratio of those corresponding sides allow us to come up with a statement of proportionality. This is going to allow us to find the scale factor. So remember, for them to be similar, they have to have corresponding angles and proportional corresponding sides, congruent angles and proportional corresponding sides. So let's look at the sides. I have, oh, I'm so running out of colors now. Those are corresponding sides. So I have AB corresponds to PQ. Actually make this smaller so I can do the values underneath. So can I look at the ratio of the length of the sides? AB is what? 2. PQ is 4. All right, let's look at another corresponding side. I have BC corresponds to what? QR. So BC corresponds to QR. BC is 3, QR is 6. And I'm saying these ratios are equivalent. Okay, let's now look at CD. CD corresponds to what? RS. CD's length is 2, RS is 4. And then last but not least, the corresponding sides, I have AD and PS. AD is 3, PS is 6. Now, notice, I'm saying these are equal. If I reduce each of these ratios, what am I going to get? They reduce to what? There you go. That's your scale factor. So your scale factor is the ratio of the length of two corresponding sides in a polygon. So what you're going to do is you're going to pick, to find the scale factor, you're going to pick corresponding pair of sides. You're going to write the ratio. You're going, ratio. You're going to reduce the ratio. And that reduced ratio is your scale factor. Once we identify the scale factor, we can find missing pieces to the similar figures. Yes, Jackson.
Wait, what's that? Like in the sandwich between pick corresponding pairs of sides and reduced ratios?
Right ratio.
Oh.
And I don't know why I always write it N. So, pick, yes, ma'am. I'm sorry?
Like, could the answer also be 2?
Yes, so you can pick the pairs and write larger to smaller. Absolutely. So in this case, I could have done PQ to AB, and I could have done QR to BC, but you have to make sure you always go from figure to figure, right? Corresponding pairs within figures. So if you list the larger one first in this case, you would get a scale factor to be 2, and that would be yet another scale factor. You would just have to define the original. I would have to see the original ones that you're working with. So that's why you would label this, and then you would show me the fraction corresponding to that with numerical values, and then you would get your scale factor. Absolutely. Absolutely. Did everybody get that? Okay. So in this case, if I'm comparing the smaller to the larger, the ratio of the smaller to the larger, I'd get the scale factor. If I'm comparing the ratio of the larger to the smaller, and remember we can do it A to B, A to B, A to B. So depending on which you choose to be A and which you choose to be B, it doesn't matter, but you have to identify that. Good. All right, let's go ahead and use this information. Let's find the scale factor, and then let's go ahead and answer a question based on that. So you have been given 2 triangles. So I'm going to draw these triangles, and I'm going to pay very close attention to the order in which I draw and label these vertices, because I am being told that these 2 triangles are similar. So the first one I have is triangle ABC. So I'm going to say A, B, C. And I'm saying, and these may or may not be drawn to scale, I'm just drawing them and labeling. That is similar to triangle DEF. So I have to start here, D, E, F. So I've drawn my 2 corresponding triangles, similar triangles. Now, I know that AB is 12. So AB is 12. I know BC is 20. Again, I don't really know what I'm going to have to use, but let's just label what we know. Oops, BC is 20. I know AC is 16. Ooh, I know all the lengths of that triangle, of the sides of the triangle. Now, let's go to the second triangle, DEF, and see what we've been given. We have been given that DE, what color have I not used? Oh, heavens. DE is 9. And I know that DF is 12. Oh, guess what we're finding? The unknown, we're finding EF. So if I'm looking for EF, oops, why do I have so many oranges? I'm going to call that X. So I need a scale factor, and then I need to find the length of X, which corresponds to which side in the other triangle? BC. So the first thing I want to do is I want to pick a pair corresponding sides. Doesn't matter. So if I look at the first triangle, so in the first triangle, in triangle ABC, I'm going to choose AB, which is 12. In DEF, so notice I'm going from this triangle to this triangle, but I could go the other way. DEF, what is the corresponding side to AB? DE. And the length of that is what? 9. Guess what I have? I have a proportion, right? Now, if I wanted to simplify 12 over 9, what would it reduce to? And what is that called? It is an improper fraction. Ooh, it looks so fancy. But what is that in terms of the similarity? This is your scale factor. I love that you said improper fractions. This is your scale factor. Now, again, if I had chosen to represent DEF to ABC, my scale factor could be the reciprocal, 3/4, but that's not how I did it. So here's my scale factor. I'm going to use this scale factor to allow me to set up a proportion to solve for X. So set up a proportion. So again, I'm going to do ABC to DEF because that's the way I chose to determine the scale factor. So I said 4/3 was my scale factor, and I'm going to set that equal to, well, X is what I'm solving for in triangle DEF, and BC, which is 20, is what I know in the corresponding similar triangle. So all I have to do is solve that proportion. So remember, cross multiply. So 4x equals 60. Divide each of those by 4 implies x is what? 15. So we found the scale factor to be 4/3 because of the way we chose to write the ratio of the two triangles. And then we found EF to be 15. Now there's a theorem. The theorem states that if two polygons are similar, then the ratio of their perimeters is equal to the scale factor or the ratio of their corresponding sides. The ratio of the corresponding sides, we said, reduces to the scale factor anyway. So if I'm given two similar triangles, so again, I know they're similar because I see the tilde, and I know what it means for them to be similar. I can find the perimeter of DEF by using what I know in ABC. So what do I have to do first? Well, let's go ahead and set up a ratio. So I have my ratio. We can choose any lengths we want. I'm going to go ahead and choose AC to, what's the corresponding side in the green triangle? DF. So that means I have 40 to 60. And if I simplify the ratio of those corresponding sides, what do I get to be to my scale factor? Okay. So this is my scale factor. And now let's look at the perimeter of triangle ABC. So that is 19 plus 34 plus 40. So what's the perimeter of ABC? 93. Now, again, I'm looking at the blue triangle. So triangle ABC to triangle DEF. I'm going to set up a proportion. So I write my scale factor, and that's going to be equal to, well, if I'm solving for the perimeter of the green one, green triangle, I'm going to take the perimeter of the blue triangle over, I can call that P, perimeter of the green one. Cross multiply, so that's going to give me 2P equals 3 times 93. So 2P equals 279. Then how do I solve for P? Okay, divide each side by 2. So I get the perimeter of the green triangle to be what? You can give me a decimal equivalent if you want. I mean, that would be a nice improper fraction, but can you give me a decimal equivalent? Y'all should be able to do that. If not, get your calculator. I don't know what. Huh? Does anybody disagree? Oh my gosh, y'all should be able to do this. Yes. So that's the perimeter. So we could say the perimeter of triangle DEF is 139.5. Okay, let's take a look at the next similar polygons. Again, I know they're similar because of the symbol. Let's take a look at how we're orienting these because they don't look, you know, exactly in the same representation. So I have SMAL, SMAL. So I'm starting here and I'm going this way, right? And that is similar to BIGE. So notice that I'm starting here and I'm going this way. So let's take a look at the similarity that we have. Again, pay attention to the order. So I've been given angle measures, and I know similar polygons have the angles, corresponding angles congruent, right? So let's take a look at what we know. So let's start with the vertex that they started with. What angle is corresponding to this? No. So angle B is what degree measure? So what angle corresponds to angle M? Y. So Y is what? 83 degrees, right? Do you see that? It depends on where you start. You have to look at corresponding angles, corresponding sides. Order matters. Order matters in your similarity statement. Okay, I'm gonna need that space, so I'm taking it back. All right, I need to find X. So in order to find X, what might I want to find first? This a proportion. So, well, I'm gonna look for the scale factor, right? And to find the scale factor, well, I have to choose. Am I doing blue to green or green to blue? Okay, why not? So I'm starting with SMAL, and I'm writing a ratio of that to BIGE. Okay, so for SMA, let's look at, I don't care which one we want to use. What do we want to use? LS. Oops. LS is what? 18. And you said write that as a ratio to what in BIGE? I agree with you. And the length of EB? Reduce that fraction? And that is your scale factor. Again, if you had chosen to do the green, BIGE to SMAL, blue, our scale factor would be 4/3, but this is why you're showing all of this. So I see where you're getting it. Okay, so now that I have my scale factor, I can find X. So I'm starting with my scale factor, and I'm setting that equal to, if I'm looking for X, what is the corresponding side in the blue? Okay, and then I'm just cross multiplying. And what is X? What? Do we agree with that? What? 84 divided by 3. What is 84 divided by 3?
28.
Y'all know how to do this, right? We okay with that? Okay. I'm gonna draw some pictures. I have a 4x6 photo. So I'm gonna say my width is 4, my length is 6. Oh, it's inches. And I want to reduce it to fit a frame that is 1.5 inches wide. How long will the reduced photo be? So I'm looking for the length here. So let's set up a proportion. So if I'm looking at width to length, that's one way I could do it. The width of the blue, that our original photo is 4 to 1.5. Oops, I wrote. Yeah, I was trying to show you something else that's coming. Never mind, let me take that back. I kind of gave it away, but it's okay. So width to length, sorry, equals width to length that I'm solving for. Now, this is going to allow me to solve for L, but is there another way I can set up a ratio that would allow me to also solve for L? And this uses one of those properties of proportions. Yeah, I could have done blue. So I could have done the original one, 4 to 6. No, sorry. I could have done 4 to 1.5 and set that equal to 6 to the length. Now notice what stays the same and what's changing from these two representations. In the first one, do we remember what these are called in the proportion? Oh, I can't hear you. What are these called, these values? The extremes, right? The extremes don't change in each of those in each of those proportions. But what is changing? The means. So isn't there a property that says I can interchange the means and get the same answer? Absolutely. So there are different ways to do these problems. As long as you're doing them and using the properties correctly, it's okay to pick and choose which method you want to use. Either way, so if I did the first one, it would be 4 times L equals 6 times 1.5. So 4L equals 9. So L equals 2.25 inches. But notice if I had done it this way, 4 times L equals 1.5. The commutative property of multiplication is saying that those are equivalent. Those are equal, right? So I'm going to get the same answer either way I do it. Ugh. So of course, this is a word problem. You would say the reduced photo would be 2.25, and you'd have to put your units. Okay, let's talk about corresponding lengths in similar polygons. Corresponding lengths in similar polygons. If you have two polygons that are similar, then the ratio of any two corresponding lengths, and when I say corresponding lengths, they could not only be the lengths of the sides, they could be the altitudes, they could be the medians, etc. Lengths in the polygon is equal to the scale factor of the similar polygons. This is quite exciting. So I have triangle TPR. TPR. Again, I'm starting here, and I'm going this way. That is similar to triangle XPZ. Starting here and going this way. So I see some congruencies, right? Just for kicks, let's talk about them. These are similar fingers. They're similar figures. So what is the corresponding angle that is congruent to angle T? X. Good. What is congruent to angle R? What angle? Z. What is congruent to this angle? To TPR. What is congruent to TPR? Okay. So I know a lot of information. So the first thing I want to do is find the scale factor. Because ultimately, I want to find this. Yes. So let's do, you want to do blue to green or green to blue? Okay. So blue, I know, let me go ahead and take TR. I can take any corresponding part. But if I take TR, what is the length of TR? 12. And that corresponds to what? XZ, which equals what? 16. And again, I could have chosen other corresponding pairs. So what does this reduce to? 3/4. There's my scale factor. So I'm going to use that scale factor, and I'm going to set that equal to, well, I'm looking for PS. You want to call that X? Let's call that X. And that corresponds to what value in the green triangle? 20. Cross multiply, so that gives me 3 times 20 equals 4 times X. So that is 60 equals 4X. So that means the length X is what? 15. So PS is 15. Good. Now, similarity has some of the same properties as equality and congruence. So what are those properties that it shares? It's reflexive, it's symmetric, it's transitive. So what do I mean by all that? Well, I could say if I have a triangle that is similar to another triangle, which is kind of, and I'm just going to use symbols because that's kind of where we're going with this. So I have two triangles that are similar, and I have that this little symbol, this triangle is similar to yet another triangle. If I wanted to demonstrate the transitive property, then what do I know? The blue one is similar to which one? Excellent. Okay, so those properties hold with similarity as well. So whereas we used, worked with the reflexive property, the symmetric property, and the transitive property when things were equal, those properties still hold true for similarity. So let's look at some true-false, because, oh gosh, that trips people up. Let's see which is true and which is false, and maybe talk about them. So the first one, all equilateral triangles are similar. Now remember, similarity means they're the same shape, not necessarily the same size. This is true, yeah. Because if you think about it, equilateral triangles are also equiangular, right? So if you change the side length, you're not changing, you're changing, I mean, you are changing the angles. What about all rectangles are similar? Really?
False, because, what if one pair of, what if it's like a bunch?
If you change the length, do you have to change the width in a rectangle? If you change the length, you don't have to change the width. So this is false. Right? Because the corresponding parts would have to have the same scale factor. So if you change one, do you have to change the other? If you change the length in an equilateral triangle, you are changing the angles. Similar quadrilaterals are congruent, true or false? Why? That's right. What about congruent quadrilaterals? Are they similar? Yes. What about all regular hexagons are similar? And what makes, I mean, they're regular, right? Same size, sides, and angles. Let me ask you this. Are all squares similar?
Yes.
Yes, because remember, squares, all the sides are the same length. So if you change one, you're changing all of them. So just a little hint for similar figures, when you're dealing with similar figures, you want to first find the corresponding pair that you want to work with. Then you want to set up a ratio and reduce to find the scale factor. Then you want to set up a proportion using the scale factor and solve for missing side. So that's kind of what you want to keep in mind when you're looking at doing your homework. Now, on the homework, some of it will actually just say find the scale factor. Some of them will actually tell you to set up a proportion to find the missing side. Now, I do want to talk a little bit about the quiz that is happening next class.
Wait, can you please go back to
Absolutely. Some things that if we look back on what we did on 6-4, 6-5, 7-1, 7-2, right? Because it doesn't necessarily set up the proportions. Yes?
What's the word after proportion?
Using a scale factor and solve for missing side. So if we think about what, and again, I want to stress that this is a little mini quiz. It's not hard. One thing that we talked about was label the largest or the smallest or largest two smallest angles or sides. Remember, we did it from least to greatest, and we set up that little extended inequality from last week. Other things that we did, was find possible side lengths, remember? After we set up, you know, our little extended inequality, we could look at possible lengths of triangles. Given 2, what would the third one possibly be? Because we know that the sum of 2 sides has to be greater or less than the third side. The sum of 2 sides has to be great, right. So we have to keep that in mind. Then if you are given a diagram, of course we always label it if we were writing on paper, but if we have 2 triangles, we should be able to find the largest angle or side given information. Because we know that the longer side is opposite the longer angle, right? And then lastly, you should be able to set up proportions and cross multiply and remember, keep in mind those properties of proportions. And do we remember what those properties were? Remember the reciprocal, interchanging the means. What else? Cross product, cross multiply, and that other one? Add the denominator. This is really all that's on the quiz.
Will you do the extended ratios, like the one from the homework?
The ones on the homework.
Oh, the last 2 on the homework.
Yeah, we can look at that.
What was the last thing?
Add the denominator. Okay, what I was talking about was being able to do this, right? That's what I was referring to, but yes, we can talk about that. Okay,